informative video which shows the both the construction and the working of DC generator. So I will play it for you guys.
DC generator. We know that a DC generator uses electromagnetic induction to convert mechanical energy into electrical energy. It is frequently used in houses and offices. But do you know how it is constructed? Let's try to understand this. A DC generator consists of a magnetic frame or yoke, the pole core, the pole coils or field coils, the armature core, the armature windings, the commutator, the brushes, and the bearings. Out of these parts, the pole core, the armature core, the yoke, and air gaps between the poles and the armature core form the magnetic circuit. Let's briefly describe each of these components. Yoke is the outer frame of a DC generator which serves two purposes. It acts as a protecting shield for the generator and provides mechanical support for the poles. In small generators, where cheapness rather than weight is the main consideration, yokes are made of cast iron. But for large generators, yokes are usually made of cast steel or rolled steel. Field magnet consists of the pole core and the pole shoes. It basically spreads out the flux in the air gap. Since it generally has a large cross-section, so it reduces reluctance of the magnetic path. It acts as a support for the field coils. Pole coils consist of the copper wire or strip which is wounded on the former. After getting the correct dimensions, the former is removed and the wound coil is put into place over the core. When current is passed through these coils, the poles get electromagnetized and produce the necessary flux that is cut by revolving the armature conductors. Armature core houses the armature conductors or coils and causes them to rotate, cutting the magnetic flux of the field magnet. It also provides a path of very low reluctance to the flux through the armature. It is cylindrical or drum-shaped and is built up of usually circular sheet steel discs or laminations approximately 0.5 mm thick. The slots are either die-cut or punched on the outer periphery of the disc, and the keyway is located in the inner diameter. Armature windings are mostly employed for the armature of a DC machine. They are of two types: lap windings and wave windings. The difference between the number of parallel in lap paths currents from the armature used for lighting. Commutator facilitates the collection of currents from the armature conductors and converts the alternating current induced in the armature conductors into unidirectional current in the external load circuit. It is of cylindrical structure and is built up of wedge-shaped segments of high conductivity, hard-drawn or drop-forged copper. The segments are insulated from each other by thin layers of mica, and the number of segments is equal to the number of armature coils. Brushes collect current from the commutator. They are usually made of carbon or graphite and are in the shape of a rectangular block. They are housed in the brush holder, which is mounted on the spindle. These brushes can slide in the rectangular box, which is open at both the ends. A flexible copper pigtail mounted at the top of the brush conveys current from the brushes to the holder. The number of brushes per spindle depends upon the magnitude of the current to be collected from the commutator. And ball bearings are frequently employed because of their reliability. the ball and rollers are generally packed in hard oil for quieter operations. Note that sleeve bearings are used in order to reduce bearing wear. Basically, the schematic diagram of a DC generator is as shown, and its main parts are
Okay, now let's start today's lecture. So now let's come to the the windings. So in generator there can be two kinds of winding. So first one is also called the lap winding. It's the very simple kind of winding. In these winding, so we know one coil has usually two turns. One is starting two ends. So one is the starting end, which we can denote it with S, and then there is the finishing end. So coil can be of any type, like it can be one turn or it can be many turns. But it has one starting end and one finish end. So in this lap winding, the start and finish end of the coil of an armature winding, they ends on to adjacent commutator segments. So we know these coils are usually connected to the commutator. So if the starting end of a coil, if it is connected to first like commutator segment, then it will fall on the second one. So these are the this is the three commutator segments. This is 1, 2, and 3. It's showing three commutator segments, and then we have two coils. So this coil 1, it has two sides, 1 and 1 dash. So we can see the starting end, which is 1, it's falling on commutator 1, segment 1, and then 1 dash, it's falling on, which is the finish end, on commutator segment 2. And then if we look at the second coil, it starts from commutator segment 2, this side 2, and then the side 2 dash, it falls on third commutator, and then this continue. So the reason why we called it lap winding, because if we look at its structure, we can see that two windings, they are overlapping. So they are placed at each other. They are kind of have parallel structure. So if we can categorize these lap winding into two types. So first is the progressive lap winding. So this it has been shown in the picture. So in progressive lap winding, the finishing end of the coil would fall on the forward segment. Forward segment mean if the start end is falling on segment 1, then its finishing end will fall on segment 2. So for coil 2, its start end, we can see it's falling on segment 2. So it's ending its second end, it will fall on segment 3. So this is moving in forward direction. Then we have retrogressive lap winding. So in retrogressive, we can see the starting end, it's actually falling on the forward segment, and then the finishing end, this is falling on the backward segment. So it's just the opposite of this one. So this is for one turn, and if we increase the turn, so we can see it here. Here we have three commutator turns. So first we can draw the coil 2. So for coil 2, its first side is connected on this commutator segment 3, and then its second side is connected on commutator segment 2, and then the finishing end of this coil 1, it falls on second segment, and then its starting end would fall on first segment. So they are opposite. Just the start, the difference between progressive lap winding and retrogressive lap winding is the placement of starting and finishing ends. So then lap winding looks like this. So if we have these commutator segments, so this is the commutator segment 1, 2, and 3, and in middle of these commutator segment, This black line, it shows the insulation. There can be some mica insulation layers. So we can see the first coil, it starts from commutator segment 1 and it's finishing on commutator segment 2. And then from the second coil, it's starting from commutator segment 2 and it's finishing on commutator segment 3. So this is progressive lap winding. So if let's say we have 4-pole machine, so in the case of 4-pole machine, like it has 4 magnetic poles. The main field, it has 4 poles. In that case, the diagram would be like this. So we can see these are the commutator segments. There are 4 commutator segments. And then for 4-pole machine, we can see there are 4 parallel paths. So we have brushes here. So these brushes, each brush's end is can connect to 2 commutators. And then these commutators between these commutators, we have these windings. So for 4-pole machine, we have 4 windings, armature windings in parallel. So we have 4 parallel paths. So there are some certain characteristics of these lap winding. So in lap winding, the total number of brushes which we require is equal to the number of poles. So if there is 4-pole machine, we need 4 brushes. Again, the number of parallel paths in lap winding is same as the number of poles. So the total EMF of the machine is equal to the EMF generated in any of the parallel paths. So we have like so many parallel paths. So here we can see, so we have 4 parallel paths. So if we want to determine the EMF of this external circuit, which is applying across external circuit, so it's equal to the EMF of any of the coil, because all the coils, they are connected in parallel. So if we can see the total current, so we have like one current coming in. This is the output current. So there are 4 coils. So it will divide equally between 4 coils. So each coil will carry an output time divided with 4 time currents. So 1/4 of the load current will pass through each commutator, each coil. So the main important characteristic of lap winding is they are used for low voltage and high current rating machines. So why this is? Because we can see its structure. So lap winding has so many parallel paths, but not so many coils are connected in series. So we know if coils are connected in series, then their EMF get added up. But if they are connected in parallel, they can handle more current. So here, they have the ability to handle more current, but their EMF is less. So that's the reason they are used for low voltage and high current rating machines. Then we have the second kind of winding, which is called the wave winding. In wave winding, the coils are simply connected in series. Like we have, so the finish of first coil is placed at the start of second coil, which is placed at a distance of 2 pole pitch away. So pole pitch is the number of armature conductors per pole. So we can, if we have 4 poles, so what we will do, we will place the winding of the start end of first coil on segment 1, and then the finishing end of first coil, we will place it at the length of 1 pole pitch. So let's say we have like 16 conductors per pole. So after 16 conductor, we will place the second conductor for that, which we connect. So in this case, if we can see, this is for 2 turns. So first turns, and then we have the second turn, and there is some distance between them. So that's, in the same way, the turns can get repeated, and we can obtain a series connection. So if we look at the equivalent circuit of wave winding, we can see there are only two parallel paths. So in wave winding, compared to the lap winding, in lap winding, the parallel paths are same as the number of poles, but here in wave winding, we will have only two parallel paths. So it's the series connection of coils. So if we look at the characteristic of wave winding, we need only two brushes. We don't need more because we have only two parallel paths. So we can just connect two brushes. But if we use only two brushes, then what will happen? Each brush has to carry a large amount of current, and the commutator segment, they must be large. So the second thing, depending on our design choice, we can use more number of brushes, which is not essential, which is a kind of optional. And by using this more number of brushes, we can reduce the commutator length. So the main characteristic of this wave winding, which is different from lap winding, is that the number of parallel paths between the positive and negative brushes is always 2. In lap winding, the number of parallel paths are equal to the number of poles, but here the number of parallel paths, they are always 2. They are independent of the number of poles. So again, the total EMF of the machine is equal to the EMF generated in any one of the parallel paths. We have two parallel paths. So if we know the EMF of one parallel path, we know this is the EMF across the load. So in this case, we have only two parallel paths. So current will equally divide between two parallel paths. So the load current, half of the load current will pass through each of the coil. So as we can see, this winding has series nature. So we know this in series, the voltage keep on increasing, but the current is limited. So this wave winding is used for when we have requirement of high voltage and low rating machines. So now for the transformer, we have already, previously, we have derived the EMF equation for transformer. But now what happens for a DC generator? We know in DC generator what we are doing, we have a main magnetic field, and in the main magnetic field we have an armature rotating. On armature we have wound some coils. So once we rotate the armature, so what happens? The flux keep varying, which is passing through the conductor, and then some EMF is induced in the conductors. So in this section we will look at how we can drive the EMF equation for DC machines. So for that, we need to remember some certain concepts first, some certain terminologies. So number of poles. So we know the pole, like machine pole is like north, south, and again let's say north, south. There can be so many. So in a machine, so this is 4-pole machine. So it will contain 4 number of poles. So there can be 2-pole machine, there can be 8-pole machine. So in order to represent the number of poles, we will use P. And then for flux, same as in transformer, this is now this is very important. This phi is the flux per pole. Like this pole is generating its own flux, this pole is generating its own flux. So once we are talking about this phi, so this is the flux per generated by unit pole. Then Z, Now this is very important, this total number of conductors. We know armature consists of coils, right? So each coil consists of number of conductors. Like let's take the example of a simple coil. Let's say we have this simple coil, we represent it like this way, which has side 1, 1 dash. So if we look at the number of conductors for this one, they are 2. So this is first, let's say A, and this is B. So it has 2 conductors. But then each coil, now this coil, it is 2 conductors based coil, but it can be more than 1 conductors. How? Like we have so let's say this is repeating. So 1, 2, 3, 4, like 2 coils, they are connected in series. So now the same, there is one turn, we can call it one turn or coil. So it has now 4 conductors, A, B, C, D. And then these conductors, they can also be connected in parallel configuration, like in lap winding. So once we call the total number of armature conductor, it means the total number of wires. Like we have this kind of armature. So here 1, and then we have second. So this is one conductor, this is second conductor. Understandable? So there can be so many parallel paths, and maybe this is not finished here, maybe it's continue like this. So this is one coil. So this is one coil which has 2 windings, turns, but it has 4 conductor sides. So by mean the from total number of conductors, we mean 1, 2, 3, and 4. So on. How many are these conductors? So this conductor is this to this. This we call it one conductor. So August, there is no brush. Oh. So these concepts are very important, because if these concepts get confused, then we cannot proceed further. So then we know the armature in a DC generator, the armature is rotating. So it will have some, there is some speed with its rotating. So we can denote it with N. Now we cannot confuse this N with the number of turns. So it's the rotations per minute. So this is the armature speed. Now then we have another terminology, which is a the number of parallel paths in armature. In lap winding, we have seen the number of parallel paths, they are same as the number of poles, and in case of wave winding, the number of parallel paths were always equal to 2. So once we know these, so now let's say we have one conductor. We have these poles. Let's say this is north, this is south. Again, this is north, we can call it south. Now let's say we have one conductor. So conductor would be, we can present it like this. So this is, let's say, current coming in, coming out. So this is 3D. So we have just taken the front view. Let's say it's rotating, right? So once it's rotating, how many poles it's facing? It will first face this pole, then it will face this pole, then it will face this pole, then it will face this pole. So total flux cut, we have already seen phi is the flux per pole. So once it does 360-degree rotation, so how much flux it's cutting? It's cutting 5 times this number of poles. Here it's 4, so 4 pi flux it's cutting. Its flux is changing by 4 pi. But here for general we will see so flux cut in one revolution, it would be equal to flux cut by moving in the, like there are 4 poles, so we can divide them into 4 quadrant. So if it's moved in 1 quadrant, so what will be flux cut? It would be phi. But now it's completing the 4 quadrants. So we have to multiply it with t, number of poles, because they can be 2. If they are 2, then segment 1 it will have flux phi, and then again the flux would vary by another phi. So p times phi, flux per pole, multiplied with the number of poles. So now there is the time taken to complete one revolution. So we know n is the speed of armature in revolution per minute. So this is equivalent to frequency. We know frequency, it's 1 over s second, time in second or minute. So n is like this. So in order to calculate time, we have to divide 1 over n. So time t is equal to 1 over f, right? But now the thing is, if we calculate like this, it will calculate us the time in minutes. So in order to do it in second, we have to multiply with 60. So this is time in minute. So each minute has 60 seconds. So we will multiply it with 60 and it will become second. So now average induced EMF in one conductor. So we know the formula for EMF. E is equal to d phi over dt multiplied with n. For this is now for the number of turns. This is not for the revolution per minute, not to confuse. But here for one conductor, n is equal to 1. So we d phi over dt, we have to divide it. So what is d phi here? We know we have taken one revolution. So during one revolution, the total flux cut is, change in flux is p phi. So E is equal to p phi. So p phi is the d phi, change in flux. Now we have to determine what is the time taken. So now this is very important. We have taken one complete rotation. So for one complete rotation, this is the amount of flux cut. Then we have to divide it with the amount of time taken for one rotation. Very important. We are taking one complete 360 rotation for calculation of our EMF. So here we know this is 60 over n time taken. So 60 over n, so it will be P phi n over 60. So this is for one conductor. But the thing is, we know armature has so many conductors, Z number of conductors, but there are A number of parallel paths in armature. So A is less than Z. So in that case, so let's see, we have something, we have some windings here. So this is two winding in series, and then there is the dot. Dot means they are being extendable, right? And these are connected, the same number of windings here are connected in parallel. And then there is another dot, like it's continue, and then it's again continue. The number of windings which are parallel, they are again continue. There can be so many. So this is generic. So now we have so many windings which are connected. Some are connected in parallel, some are in series. So far what we have done, we have calculated the EMF of this coil. E. For one coil we have calculated it. But we know the brushes are connected like this, plus, minus. So within the brushes we have so many windings which are in parallel. So parallel winding don't influence our EMF, the series winding does. So we now need to determine how many windings are in series, how we can do it. This total number of windings, they are equal to Z. Z is 1, 2, 3, 4, this is the total number of conductors. So this is one conductor, we can call it. This is second conductor, third, fourth, so on. So Z is the total number of conductors. So how many of them are connected in parallel? This is the A. A is the number of parallel path. So this is A. A is the number of parallel path. What we want to do, we want to determine how many conductors are in series, because we want to determine this EMF. So this is for one conductor. So we need to determine this number of conductor in series path. How we can do it? Number of conductors in one series path. So this is one series path, and all of these series paths, they are connected in parallel, so their EMF is same. So number of conductors would be simply be total number of conductors divided with the number of conductors for number of parallel paths. So then we can obtain this number of conductors here. So why we are determining this? Because we want to find out this total voltage produced. So now average induced armature. So how much would it be? Simply for one conductor we will multiply it with Z over A, which is the series number of paths. So P phi n over 60 multiplied with Z over A. So, this is the formula for this voltage, the terminal voltage, which is V naught, we can call it. So, we can find out this voltage. So, this is Z over A. So, I will remove this. So, the total terminal EMF which we obtain, its formula we will further modify it to reach to some certain conclusion. So, the formula which we have determined, this is for E, which is the, sorry, this is not V naught, this we can call it E. Capital E, this is giving us the armature EMF. So, we have already calculated its formula, it was P phi total flux per P Z phi n over 60, and then this is A. Z over A the number of series path, P phi is the total flux, and this is the rotation per second. So, here we can further solve it, because this n over 60 so we know n is equal to revolution per minute. So, here n is equal to revolution per second. So, we can denote it with n. So, then we can further simplify it, P Z phi A into n. So, now let us say our DC machine is fixed, generator is fixed. So, for fixed, number of poles constant, right, and Z over A they are also constant, because we have already fabricated the machine. Z over A constant. So, what we are remain with, E is directly proportional to phi and then n, flux per pole and then the revolutions per second, or we can denote it with E is equal to k phi n. Here k is equal to Pz over A. Or we can call it E is equal to K1 phi n. Here K1 is equal to (60A). So, instead of n we have represented in terms of, so here we have just put place this value of n instead of n here. So, we can see E is equal to phi n, is directly proportional to phi n, but n is the rotation per minute. So, from this rotation per minute we can denote, instead of we can write this omega, we know this is equal to 2 pi f. So, omega we can represent it is as 2 pi. So, instead of F we will represent with N, but this is the revolution per minute. So in order to represent it in terms of rotation per second, we will just divide it with 60. So this is the omega. So we can say E is directly proportional to, because omega is directly proportional to, this is constant, this is constant, this is constant. So omega is directly proportional to N. It means here this E is equal to directly proportional to phi into N. So instead of N, it's equal to, we can write it as omega. So what we can see that the induced EMF in generator is directly proportional to two things. So first is the phi, which is the flux per pole, and the second is the frequency of its angular moment of armature. So if we increase phi, we can increase the induced EMF, and if we increase the omega, we can also increase the speed of induced EMF. So this EMF is induced in both the generator and the motor. So because both are rotating, in generator we are rotating the armature, and because of rotation of armature we obtain the EMF. In motor, what's happening? In motor we are applying some voltage, but once we apply some voltage, the coil armature will rotate because of applying flowing current, and then again this armature will create its own EMF. Same as in the case of transformer. In the case of transformer, we have read that the transformer has like this. If we apply voltage, we have these turns. So once we apply this varying voltage, so what happens? The current flows through this coil. So what this current does? It creates EMF of this coil. So same is in the case of a motor or generator. The EMF formula is Eg is equal to this EB. This EB is for a motor, and it is called the back EMF. Why it's called the back EMF? Because this is opposing the supply voltage. So here, so in motor we have supplied some voltage. The EMF which is produced, it is against that voltage. So it is called this back EMF. But their formula is same: Pz phi n over 68. So it's directly proportional to phi and n. So this is the EMF equation. Then we know once so this is the magnetic property, like something is rotating and it's cutting some flux, so EMF is induced. But in motor and generator there is the another very important parameter, which is the torque. So now we will talk about the development of torque in this DC machine. So now let's consider we have a conductor. We have this armature, it's its front view. On armature we have placed one conductor, and it's rotating in clockwise direction. So this is the force which is applied on it. So because this conductor is carrying the current and it's placed in magnetic field, some force will act on this conductor, which will produce this turning moment or torque. So this torque we can represent it with this cross product of force and its this radius. So this torque is produced because of electromagnetic effect, and we call it electromagnetic torque. So in order to determine this torque, again same as previous, P number of poles flux per pole, and then so don't confuse R with L. In 3D, we have armature like this, and then this conductor is placed here on one, then there can be many slots. So this R is the distance of this armature has this cross section. So this distance is called radius. This is the rotation, the radius of its rotation, because this armature will have some shaft and it will rotate around its shaft. So this is the rotation radius, but the conductor length, it's this much. So this is the conductor length, it's in meter. So Z is total number of conductors So what does mean by total armature current? So armature has like this is the conductor, this is the conductor, and then there is the conductor continues. So then we have so many parallel paths. So each parallel path, so we have connected our armature. So this is the output which is we are obtaining from armature. So this is the total current IA. So it is being divided here, being divided here, being divided here. So this is the total current. It's coming to the armature conductor from one point entering and one point it's leaving. So then A parallel path 1, 2, 3 and so on. So now this is the conductor which is moving in field and it's carrying a current. So this conductor are carrying current I. We have already studied it. It's equal to, we can denote it with F, it's BIL. We have, let's suppose we have this is the magnetic field in which a conductor is placed. So this is the field strength, which is magnetic field density, and I is the current flowing through this conductor, and then this is the conductor length. This is its length. So in that case, we will multiply it, we will obtain the force, average force on one conductor. So now the torque developed per conductor, the torque which is being developed, it's equal to force into radius, BIL into R. So if we need to determine the torque, so it's also equal to F into R, force into radius, and force is equal to BIL. Developed in armature, it would be equal to, we have to just multiply the number of conductors, which is Z, with FR. So if Z is 1, if the total number of conductor, like we have seen one conductor case, then it would be simply equal to FR. If there are 2, then 2 times. Or Z and then LR. So now there are a number of parallel paths. So this is the total armature current. So current through each conductor it's equal to, we can call it I, it's equal to IA over number of parallel path. So here this is I from one conductor, it's passing through this conductor and this conductor as well. Same current is passing through this conductor, but through each conductor, if we are going to determine the current, it would be like this. So now we have to further find the value of flux density, put it in here. We know average flux density, it's equal to B is equal to phi over A. A is the area of cross section. So area of cross section, let's say we have again 4 poles, N, S, N, S. So this is the conductor which has a radius and it's rotating. So far now we have determined this flux density. This is because of one pole. So area under the influence of one pole, we know that there are 4 poles. So this area is this much cross section area. So for 260-degree rotation, if we going to determine this area, this would be equal to 2 pi RL. So R is this radius and then the length of conductor, because this is extended. This is being extended. So 2 pi r multiplied with L. But the thing is, this flux density, we are calling it flux density per pole because this is phi over A. Phi is the flux per pole. So here, this cross sectional area we have to find out for one pole. So for one pole, we have to divide it with number of poles, very important. Like there are 4 poles, then cross sectional area we have to take only this much, because this much cross sectional area, like there is this north pole, if we take upper north pole, it has this much influence, then this has this much influence. So we have to take this cross sectional area. So total cross sectional area of cylinder divided with the number of poles. So we can find out this area of cross section, and from this area of cross section, B is equal to phi over A. We know this, and phi is, and for A we will put this phi P over 2 pi RL. Or we can find this is the total flux density. So if we are going to find the total flux density, if we are taking the total flux, then we have to take this much area, the total this area. Now we know the equation 1, which was equal to ZFR, the torque developed in the armature. This is the number of conductor in armature multiplied with force into this radius. So here Z we have this equation, we can further solve it. Z B I L R. So Z is here. So instead of this B, we can represent phi P over 2 pi RL. And then instead of this I, we already know this I is equal to IA over A, because this we don't usually know these currents. We know this terminal current. So if we have this terminal current, this is the armature current, and then we have the number of parallel path, we can find out this current. So instead of representing in terms of this current, we have to represent in terms of this and parallel path. So IA over A multiplied with L multiplied with R. So this is the our torque formula. So L will cancel out with L, R will cancel out with R. So we will remain with this P Z phi I A over 2 pi A Newton meter. So we have determined this formula. So reason to do all of this, because this was the generic equation. This equation we already derived its generic equation. But once we are solving for DC machine, we don't have these values. We don't have this current value. We have instead armature current. Then we have the number of parallel path, then number of total conductors. So we have to represent in these noun parameters. So then there is the famous formula for the power developed in the armature. In the armature, we can see this is the electrical power, right? This is the voltage, and this is the armature current, and this is the armature EMF. So if we multiply it with them together, we can find out the power. In armature, it's equal to E into IA. But this is the electrical power. And then there is the mechanical power, because armature is rotating. So armature conductor, they have electrical power, but this power is translating into mechanical power in the form of this rotation. So that power, this we can denote it with omega T, torque into, this is the angular frequency. So we already have determined the omega. We know omega is equal to 2 pi f. Here f is equal to n over 60 revolution per minute divided with 60. So omega is equal to 2 pi n over 60. So EI, which is the electric power, is equal to mechanical power, and the mechanical power is equal to 2 pi n over 60. This is for omega into our torque. And you know, for this E, this is the induced EMF. For this induced EMF, we have already found its formula before in previous section. So from this previous section, we can find, put its value and solve it further. So in previous section, we have found out that this is equal to phi z and p over 60a. So from here we can put it in this equation. So it would become phi z and p over 60a multiplied with ia is equal to 2 pi n over 60 multiplied with T, which is the torque. 60 cancel out, n is cancel out. So we can, from here we can determine this torque equation. It's equal to phi Ia over 2 pi. So by solving this torque, we can we will take them here, and then we can obtain this multiplied with P z over A. Once we determine this EMF equation, we have this term in that. So this term is constant. For particular machine, we have the number of conductors, noun, they are constant. Number of poles, they are constant. Number of parallel paths, they are constant. So we can take it as constant, which is equal to K, and then we can write it, torque is equal to K phi Ia over 2 pi and again we know 2 pi is also constant, so we can instead write it T is equal to K2. This is second constant because in EMF we have used K1. So in order to distinguish that, we can say it K2 into phi Ia, and K2 would be equal to Pz over 2 pi A. So this is K2. So from here we can see that the torque developed, it's directly proportional to armature current multiplied with the flux. So once the conductor is carrying some current and it's in a magnetic field with flux phi, so the torque which is developed on this conductor, which will make this conductor rotate and this armature, it's directly proportional to the amount of flux and the armature current. So again, now there is what would be the direction of this rotation? It will depend on two things. First of all, the direction of this magnetic flux. It's like it can be this direction or it can be reverse direction, and then the current flowing through this coil, its direction. If we change them both simultaneously, the torque will not change. But if we change one direction while the other is same, our torque will be reversed. So now there are some interesting example problems related to the topics which we have studied about EMF induced in armature and the torque developed in the armature. So for first example, we have a 4-pole DC machine which has 144 slots in the armature with 2 coil sides per slot. Now this is so we know the armature is kind of cylindrical object in which we have cut down some slots, and in these slots we place the conductors. If we draw an armature, the front view, it would be circular, but there are some slots, right? The armature is like this. So now they are telling us that a 4-pole DC machine, so total number of poles we know P, it's equal to now 4. It has 144 slots. So these are the slots, 1, 2, 3, 4, so on, 144 slots. Total slots with 2 coil sides per slot. In each slot we have 2 coil sides. So let's say this is the coil, and then there is the second coil. So this is side A, B, let's say this is C, this is D. Okay, this is B, this is C, this is D. So 2 sides per slot mean this C and B, they are overlapping. So this C and B, 2 conductors are in 1 slot. So understandable. There are total 144 slots. Each slots have 2 sides. But now the thing is, each coil has 2 turns. 2 coil sides per slot, and each coil has 2 turns. So this is 1 turn coil, 2 turn coil mean this is 2 turn. Each coil has 2 turn now. So total slots and coil sides in each slot. Two, and each coil has 2 turn. Two. So from here we can find out our Z. Z is the total number of conductors. So each there are 2 sides in each slots, and each coil has 2 turns. So per slot there are 4 conductors per slot, and there are 144 slots. So how we can determine the Z? Z would be equal to this total slots, which is 144, multiplied with coil side in each slot, multiplied with the number of turns for each coil, which is 2. So that's how we can determine the total number of conductors. The flux per pole is 20 milliweber. This is the flux per pole, 0.2 Weber. So now the armature is lap wound. Why they have given us this lap wound, and which information we can extract from this? We know in lap wound the number of parallel paths, they are same as the number of poles. So because they have given us this lap wound, so A, which is number of parallel paths, this would be equal to number of poles, this would be number of equal to poles, which are 4. If they have told us this is wave winding, so then number of poles, they don't matter. We will ignore them and we will take our number of parallel path as 2 always. So what we have to do, and the rotation is, which is the N, it's 720 revolution per minute. So how we know this is capital N, not the small n? Because they have given us the revolution per minute, not the revolution per second. So what we have to determine? This is the induced EMF across the armature and then across each parallel path. So we know this is the generator, so Eg here, it would be equal to, we have already determined its formula, which is phi Z N P over 60A. Now this is very important. This N over the 60, we have given it here to make it in seconds. If they have given us this revolution per second, so in that case that is N. So N is already equal to N over 60. So we will remove 60, then we will put just simple this value here. So we have been given all these parameters. So phi is 20 10 raised to power minus 3. Z, the total number of conductors, that comes out to be 576 multiplied with 720 revolution per minute. We have to divide it with 60. That's why we have put 60 in formula. Then P, number of poles, which are 4, divided with 60 into number of parallel path, which is again 4. So pole and parallel path, they are cancel out. So our Eg, it would be equal to 138.24 volt. So important takeaway from here is to understand that this is the 4-pole DC machine which has lap winding. So for lap winding, the number of parallel paths are same as the number of poles. So now there is second example. So I will not solve it there. We can go through here. So there is a 6-pole machine. So poles are given which has an armature with 90 slots, and so now the slots are 90 and 8 conductors per slot. So this is very easy. We can determine the total number of conductors by multiplying the number of slots with the conductors per slot. The flux per pole is 0.5 Weber and rotation per second and it rotates at 1000 RPM. We have to determine the induced EMF if winding is lap winding or wave winding. So the formula remains same. For lap, A is equal to 6. For wave, number of parallel path A would be is equal to 2. So we can, for the same, we can, and again we can multiply with it, we can get Z. So here we can determine it first for lap connect. So A is 6, so it's 600 volt being developed, the induced EMF. But with wave connected, because the parallel paths are less, number of conductors are same for wave winding, but parallel paths are less. So less parallel path means there are more conductor in series. So what will happen once there are more conductor in series? The induced EMF, it will increase. So we can see here it's 3 times the induced EMF in the case of lap winding for the wave winding. Okay, so we can take a 15-minute break, then we can continue. So now this is the problem 3. So there is 8 pole generator which has wave wound armature. It has 51 slots and each slot contain 16 conductors. So the voltage required to be generated is 300 volt. So what would be the speed of coupled prime mover if flux per pole is 0.05 Weber? So basically we have been given the EMF and other parameters, and then we have to find the speed of prime mover. Now once we have found it for wave wound armature, then they are saying if the armature is now rewound using as lap wound machine and run by the same prime mover, which we already determine its revolution per minute. By using that revolution per minute, we have to find out the generated voltage. So there are 8 pole, P is equal to 8, and Z would be equal to, so we know the slots are 51 multiplied with each slot contains 16 conductors, so we can find out this as 816 conductors. So now the winding is wave wound. So for wave wound, number of parallel paths, they are 2. They are not depending on these number of poles. And EG is equal to 300 volt. So we know EG, it's equal to phi Z N P over 60A. So from here we can determine the N. We can put the value of phi, we have Z, we have P, and 60 we have the A. So we find out the revolution per minute, so they will come out to be 0.3. Now we are assuming that now the winding has changed into lap, and we are rotating our prime mover, which is armature, with the same revolution per minute. So this was the result for first part of our problem, but this is now given thing for second part of problem. So for lap winding, now this is the same formula. Where N has been given, phi is given, Z is same. But now the A, because this is lap winding, now A would be equal to 8. So once the A is equal to 8 and N is this term, we can determine again the EMF induced, which was given in previous case. So once we determine this EMF induced, that comes out to be 75 volt. So this was expected because now the windings are the lap winding, so EMF is reduced. So first case the EMF was 300 volt for these number of rotations per minute, but now this is only 75 volt, the produced one. Now this is very interesting. So here they are saying a 6-pole lap wound armature rotating at 350 revolution per minute is required to generate 260 volt. The effective flux per pole is about 0.5 Weber. This is the actual flux. So if the armature has 120 slots, we have to determine the suitable number of conductor per slot and hence determine the actual value of flux required to generate the same voltage. So let's ignore this, the actual value of flux required to generate the same. Let's ignore this and just determine the number of conductors per slot. So the number of poles, they are 6. So see, this is lap wound. So A is equal to P is equal to 6 and induced EMF is equal to 260 volt and phi 0.05 Weber. So we know this formula. And there are how many slots? The armature slots. So we have to find out the number of conductors per slot. So how we can find out that? By determining the total number of conductors. Which is Z over armature slots. This is we have to determine. So for that we have to determine the Z. How we can determine? We already have this formula, Eg is equal to phi Z NP over 60A. So from here we can find out the value of Z. So Z would be come out to be this value 260 multiplied with 24 over 7. We didn't solve it because we want to obtain the fraction number later. So so this is our Z. So now we have to divide the armature slots. So number of conductor per slot, once we solve this, they would come out to be 260 multiplied with 24 over 7. You can also calculate their value, but then armature slots, how many we have? It's 1 over 120. So now the number of conductor per slots, they are coming out to be 7.43. So if we have a magnetic flux of this much Weber, which is 0.05 Weber, in order to produce this EMF, we need these number of conductors per slot. But the problem is that we cannot exactly make these number of turns. Number of conductors, they can be 1, 2, 3, 4. The full number, they cannot be fractional. So we have to take takes the next value, the bigger value. So we have to take it as 8. So now what happens once we take this 8? Now they are saying, now we have to determine the actual value of flux required to generate the same voltage. So first, for these number of turns, once we have these number of conductors per slot, we needed this much flux to produce this voltage. But in actual, once we did all the calculation, we came to know that in actual case, in practical case, we cannot make these number of turns. So then we have to increase our number of turns to 8, number of conductors per slot. So for now 8 number of turns, we have to calculate the flux value which will gives us this induced EMF. So now our Z will change. Previously we calculated Z based on these assumptions, but in that case the number of conductors were coming out to be this, not the whole number. So new Z would be, because we have fixed the number of conductor per slots, so new Z, which would be Z dash, it comes out to be number of slots which are 120 multiplied with the 8. So this is coming out to be now 960. So from here the actual value of flux required we can find out from using the same equation. It would be equal to Eg multiplied with 60A over Z and P. So this is the required EMF multiplied with 60 multiplied with number of poles which are 6 divided with Z, which is 960. So previously the Z was not 960, but here because we have increased number of turns, number of conductor per slot, so our Z is different, and N is 350 multiplied with A is 6, P is 6. So from here we can determine, and our flux now required is 0.0464 Weber. So what we can see from this example, that for actual design, the number of turns which we calculated corresponding to this flux, they cannot be achieved. So we have modified the number of conductors. So once we modified the number of conductors, in order to generate the same EMF voltage, we need less flux. So always remember, like we can do calculated design for something, but once we are going to do it practically, so practically we cannot achieve all those parameters, so we have to make some compromise. So like in this case, we cannot make the number of turns which is the fractional number, so we have to make it whole number. So once we round it off, our complete design change, required flux gets changed. Now there is another very interesting topic, which is the armature reaction. So we know in, like we have a generator, so we have a main field which is shown here, and then we have an armature. On armature we have conductors. Once the current is flowing through these conductors, the armature produces its own magnetic field. So once we have a main magnetic field and then armature carrying current has its own magnetic field, once two magnetic fields overlap, then there will be some change in a resultant flux. So this change in resultant flux, we can determine it by using this armature reaction. So the effect of armature field produced by the armature current carrying conductors on the main magnetic field, we can also call it the armature reaction. So let's consider there is a two-pole generator. So it's simple. For two-pole, we have only a north pole, and then we have a south pole, and then we have this armature which is moving freely, and then it has some conductors. So now let's say there is no current flowing through armature. There is no current through armature. How its armature current is zero? There is no load connected. In that case, so this we will have this magnetic flux flowing. It will be like this, and it will be flowing through armature. And this is the main magnetic field. We can also call it Fn. So this is pretty forward. The reason why I have make this flux tilde, because the flux is going from the armature. For this flux which is flowing through this air gap, the armature will provide it smaller reluctance path, so it will bend towards armature, but this is okay. The field is moving in the right direction. So there is no problem with this field. So this is the main field. So the main field, we can represent it by this OFM. This is the MMF produced by the main field. So in this case, now it's very important to describe two neutral axes. So one is the geometrical neutral axis. So let's see what is the geometrical neutral axis. We have this magnetic field between two conductors, between two poles, permanent magnet. This is south and this is north. And then we have any conductor. This conductor can rotate here 360. It can rotate for 360, like say clockwise. So we know the EMF induced in conductor, it's equal to VPL sine theta. So this is the velocity, and this is the magnetic field strength and its direction, and then L is the length of conductor, and sine theta is the angle between this moment and this B theta, right? Now for this one, this conductor is carrying some current. It's rotating and there is some EMF is generating in this conductor. So the geometrical neutral axis, this is the line passing through the geometrically central point between the two adjacent opposite magnetic pole. This is called geometrical neutral axis. So we have these two opposite poles. So between these poles there is one axis on which if the conductor comes, there is no EMF induced on that conductor. This is through geometry. For geometry, this is this axis. How this is axis? This is called GNA, geometrical neutral plane. Why we call it geometrical neutral plane? If two poles are like this and flux is like this, then ideally once our conductor is on this axis, like this conductor can move freely, once it's on this axis, what will happen? the velocity direction of its rotation, it's same as this field direction. So what's happening? Theta is equal to 0 and E is equal to 0. So in ideal case, the axis on which the EMF induced on the conductor moving in this field is 0 is called the geometrical neutral axis. So this is geometrical neutral point. This can or cannot be magnetic neutral point. So then there is the second term, which is the magnetic neutral axis. This is the line passing through the magnetically neutral position between the two adjacent opposite magnetic pole. This is called the magnetic neutral axis. When a conductor passes through these axes, no EMF is induced in the conductor or coil. So this is the geometrical neutral axis. We can see here that geometrically, if the flux, this flux is in this direction, then if a conductor is at this plane, there is no flux produced in it. But if our flux changes like this, it's going in this direction or this direction, then geometrical neutral plane remains like this way, but our magnetic neutral plane, then maybe the conductor have to be like this for no EMF production, because the velocity is like this and now the B is like this, then theta is 0 here. Theta is not 0 here for this kind of field. So geometrically, if we see, because these poles are like aligned like this, we can say, okay, this is the geometrical neutral point. But this may or may not be the actual neutral point. Actual neutral point is at which conductor EMF would be 0. So this actual neutral point is the magnetic neutral point. So in this case, the flux is uniformly distributed. It's moving smoothly from north to south pole. So magnetic field is well aligned. In this case, this geometrical neutral axis and magnetic neutral axis, they are same. And these axes fall like they are cutting this field by 90 degree. And then we have already talked about in previous lecture, we will put carbon brushes at this magnetic geometrical neutral plane. Why we put it here? Because once this commutator comes in contact with this brush, the coil gets short circuit. We want the coil to get short circuit only at the instance once the voltage EMF across it is 0. We cannot short a voltage source, we can short only a wire which has no current flowing. So that's why we place our brushes here on geometrical neutral axis. So in this case, because this armature is carrying no current, it has no magnetic field, there is only single magnetic field, geometrical neutral axis and magnetic neutral axis, they are falling on the same axis. Everything is well and smooth. Until what happens, we applied the load to the generator. So what will happen? The current will flow through the armature conductors, which will set up the armature field, right? So now we applied some load. It was already rotating. We applied load. So current will start flowing through this. So what happens then? Current start flowing through this. So this north pole, there are some conductors which are facing north pole and there are some conductors which are under the influence of south pole. It is rotating clockwise. So the conductor which are under the influence of this north pole, in that case, in those conductors the current will move inside. But in these conductors the current will come outside. So then we will apply right hand rule. The current is flowing like this. The curl of the curl of finger is the direction of current flow, and in that case, this is the direction of magnetic field produced. This is the downward direction, OFA. This is the magnetic field of armature. And how the flux will flow? This is very simple. We have this armature. So we have this conductor carrying current. So the flux would be flow like this, and then these loops will be formed. So the current will, the flux will flow. So now there was one main field flux. Now our armature flux is superimposed on that main field flux. So what will happen? This main field flux, which was uniform before, it will get distorted. So if we look at here, so this OFA, this is representing the armature magnetic field now. So this armature flux, it's interacting with previous flux. So what will happen? Resultant flux will change. How it will change? So if we look at here, so main field flux was like this, very uniform, but this flux is superimposed. This flux is superimposed. How it's superimposed? It's like this. If we look at this loop, it is making these loops. One loop is here, one loop is here. I am talking about these loops. So this loop's direction is like this. If we look at these loops, I'm sorry, this is the wrong direction. The direction is okay, this is coming down, and this is coming up. And here it's coming down and coming up. So coming down, coming up. So field is smooth and going. So now very important to see, observe here. If we look at, let's take first this point. At this point, in this point we can see at top, this field direction, this is FM, this is FR. So this field, if we look at these points, this field and this field, they are adding up. So it means flux is increasing at this point, right? And then let's look at these points. This flux is in this direction, this is going opposite direction. So here the flux is being cancelled out. So if we look at this north pole, at this end flux is adding up and this end flux is decreasing. So this current add up, flux add up, we have shown like this. And now this is very important term. It can be observed that the resultant flux is no longer uniform. This is not uniform. This was the uniform flux. So how this flux is behaving? It is concentrated or becomes stronger at the trailing pole tips, and it is rare or become weaker at the leading pole tips. So what are the trailing pole tips and leading pole tips? So for this north pole, this armature is rotating, right? So once this armature is rotating in clockwise, so which pole side it sees first? This one. So this pole side is leading pole side. Then what is the trailing pole side? After that it's rotate, it will see this. So this is trailing, leading, trailing, but here it's opposite. Here this is leading because it's in clockwise. So leading, decrease, trailing, increase. So this is the explanation for this one. So we can see at this is the trailing ends, flux has increased, leading end, flux has decreased. So now the resultant magnetic flux, because two magnetic flux has superimposed and the resultant magnetic flux is like this. So now it is no more in this direction, it has some angle. It has moved to this direction, and this is FM and this is FR. This is rotator magnetic field direction and this is main magnetic field direction. So the resultant flux, this is again, this is also FR. So this is the resultant magnetic field direction. It has made an angle phi. with this Fm. So we can see that because of these two field interaction, our result field is now changed. No more uniform and no more in horizontal traction. So what's happening here? Now this is our geometrical neutral axis. It remains same because it is the geometrical convention. It doesn't depend on the actual condition. This is between north and south pole, where this is right angle to north and south pole. At field it's the right angle. This is neutral axis, because if we look a conductor at this, the conductor movement would be like this, and it should have zero EMF induced. But here the field direction is changed in this angle. Now our actual this magnetic neutral axis, this is the actual neutral axis, it is moved to this point. This angle theta, it is also rotated by angle theta, and now it's at this point. If now see, the field is like this. Now our magnetic lines of force are like this. In this direction, they start making an angle theta with the previous. It was Fm, and now this is Fm dash. So for this one, our neutral axis was this, because this direction, and then if velocity is in this direction, there was zero induced EMF. But in this case, if we place conductor here, the conductor velocity is like this, we are getting some angle. So this is no more the neutral. So what is the neutral axis now? Right angle to this field. So this is this neutral axis, because at this axis we have conductor, they are parallel, their velocity is parallel. So very important. So now our magnetic neutral axis, it is moved by angle phi. So the conductor placed at this magnetic neutral axis, now they will have zero induced EMF. So the magnetic neutral axis is shifted to new position, which is displaced from its original position by an angle theta. So what does this shifting of angle theta depends on? So it depends on the loading condition, because the larger the load mean more current will be flowing through armature. So armature field will be more strong. So once the armature field is more strong, it will more strongly influence the main field. So our theta would be large. So now based on the new position of magnetic neutral axis, the distribution of flux would be like this. Because now these conductors have zero EMF and these conductors have EMF. So now how our armature will create its magnetic field? Again simply the right hand rule. But now axis is shifted because conductors are in this direction, so we will contain this, and then it's moved to like this, the armature field. Now the armature field has two components. So because armature field is moved like this. So if a field is moved like this, it will have two components. One is this component and one is this. And this is the angle theta. So this is its kind of horizontal and this vertical component, and this component can be like this. So this is our FAR, this is armature field, and this is FC. This consists of two components. So one is FC and one is FD. So now it consists of two components, which is one is the O is the central point here, so OFC and OFC. So it can be decomposed into two components. So OFC is the perpendicular to the main MMF. It produces the cross magnetizing effect. We will consider this later. And then OFD, this opposes the main MMF, OFM, and produces the demagnetizing effect. So what is our main field? Our main field is in this direction, right? Poles are like this. So FD is totally opposite to that field. So this field is creating magnetization, so it is opposing this. So we called it demagnetizing field. And this is the other field, which is FC. It is the perpendicular to the main MMF, and it will produce the cross magnetic effect. We will talk about it later. But this is very simple to understand. OFD, it opposes the main EMF, MMF, so it is producing the demagnetizing effect. So now let's talk about the cross magnetizing effect and the demagnetizing effect. So cross magnetizing effect, it creates a magnetic field in between the two adjacent opposite pole where brushes are placed for commutation. So these are the two opposite poles. So if we look at here, so these are the field between two opposite poles, and this is the axis where we placed our brushes. So what is it saying? It's saying the cross magnetizing effect, it creates a magnetic field in between the two adjacent opposite poles where brushes are placed for commutation. So we have this north pole, we have this south pole, and this was the original field, but then we have conductor. If we place conductor here, this was the geometrical neutral axis, but because of this shift in because of armature reaction, this is no more our neutral point now, and the brushes are connected here. So there is the field consists of two components. So one component which is making some EMF, which is responsible for producing some voltage here. This is called the cross magnetizing effect. And then the demagnetizing effect, it weakens the main magnetic field and changes the flux distribution such that at trailing pole tip the flux is strengthened, and at leading pole tips the flux is weakened. So this is the demagnetizing effect. So this is creating this field. This is creating a demagnetizing effect. But then there is another field which is making this point to have some EMF induced. Originally it shouldn't have. So this is the cross magnetic effect. So what would be the consequences of armature reaction? So the first consequence would be the sparking at the brushes. So we know we have placed brushes here, because what happens once the commutator comes in contact with brushes, like this is commutator segment 1, and then it has some insulation here, and then there is the commutation segment 2, and once brush comes here, so then it is carrying some coil, it's carrying coil. So one of coil, it gets short circuit, like let's say we have this coil. So because of this brush like this, it is getting short circuit. This is get short circuit. So originally we have placed brushes here because at this point there was no EMF induced. So anytime a coil was getting into a short circuit position, the EMF induced was already 0. So if a wire has 2 terminal and it's carrying no current, no EMF, we can short circuit it, no problem. But now the problem is brushes are placed here. So this coil, it is carrying some voltage once it gets short circuit. So because of that, we are continuously short circuiting some voltage, there would be sparking. So this sparking will occur and it will heat up the brushes and it will decrease the brushes life and also the commutator life. And then there are the iron losses. The iron losses, in iron losses we have the core losses. We know the core losses, they depend on the change in flux. So now, because first here the flux was equally distributed, the change was less. But in this case, the flux is changing. At some point it is very large, and some point it's getting smaller. This change in flux will create more iron losses. These iron losses are specifically the core losses, magnetic core loss. So now it's very important, this is important, it's about the calculation for armature ampere turns. So we know the armature reaction, it causes the demagnetizing and cross magnetizing effect, 2 effects. So due to armature reaction, let the MNA be shifted ahead by an angle theta. Let's say we have armature reaction and our magnetic neutral axis, it is shifted by an angle theta from this geometrical neutral axis. So this new position of magnetic neutral axis, it's represented by line AB. This is the line AB. And now we can draw another line CD. This is another line CD we have made, which is making same angle theta. So we have this geometrical neutral axis, and then magnetic neutral axis is shifted by an angle theta, and this is AB. So we can draw another line here. It would cross from here. This is CD. So this line is also making same angle theta. So this is the 2 theta total angle. So now this armature, we have wound many conductors on this armature on like specific points. So we can observe that the conductor lying between AOC, this is A, this is O, and this is C, and then BOD, this is BOD. Between these points there are some conductors which are lying here and here. These conductors, so these conductors, they are carrying current in such a direction that MMF produced by them is opposite to the main MMF. MMF is the magnetomotive force, which is equal to Ni, the current times the number of turns. So these conductors cause demagnetizing effect, and these turns are known as demagnetizing turn. So if we look at these turns, so what is the direction of magnetic field? It's left to right, right? And what about the magnetic field produced by these turns? Again, right hand rule, so it's right to left. So this conductor, it's producing its own magnetic field which is in reverse direction compared to this field. So this is creating demagnetizing effect. These conductors which are between these 2 lines. And then there are the remaining conductors. The remaining conductors are from this between AOD and C and COB. They produce cross magnetizing MMF and they are called cross magnetizing turn. So we have already known the cross magnetizing effect, like they are creating, first they are distorting the magnetic field. We can see it here. They are creating this kind of field which is not in line with original field. They have distorting the magnetic field. So how we can calculate the number of turns for this? How many number of turns will be placed here between these points, which will create this demagnetizing effect, and how many will create this cross magnetizing effect? So let's assume Z is the total number of armature conductors. So this armature, it's carrying Z number of conductors, and then A is the number of parallel paths we have already studied before, and theta is the angle by which MNA is shifted, this magnetic neutral axis is shifted, and P is the number of poles. So here we are using 2 poles, but there can be 4 poles, and IA is the armature current. We have already talked about it. It's the total current which is divided between parallel path. So current per parallel path or current in each conductor, it's IC, it's IA over number of parallel path. We can determine it. So total armature ampere turns. So what are the ampere turns? Current through each MMF, it's equal to NI. For transformer we have already seen this. So how we can calculate it? Current per parallel path, then total armature ampere turns, so Z is the number of conductors. So total armature ampere turns, it will be equal to IC. IC is the current through each conductor multiplied with the number of turns. We have to multiply it with the number of turns. So Z is the number of conductor. So how many conductors are making one turn? This is one conductor, this is second conductor, 2 are making. So in order to calculate the number of turns, MMF depends on the number of turns, not the conductors. So in order to find out the MMF or ampere turns, we have to the current through each conductor multiplied with the number of turns. So number of turns would be Z over 2. So total ampere turns per pole, now it's easy to calculate here. It's 2 pole, so ampere turns per pole would be half. So similarly, if there are P number of poles, we will divide it with the P. So now we can easily calculate the demagnetizing ampere turns, which is the ampere turns lying in the angle AOC plus BOD. AOC plus BOD. So we know this total angle is 2 theta. So IC Z over 2, total ampere turns per pole. Okay. So this IC Z over 2, total armature ampere turn, we can from these total armature ampere turns, this total angle is how much? This is 360. From 360, this angle is 2 theta and this angle is also 2 theta. So we will take this angle. 2 theta plus 2 theta, we will divide it with 360 and we can determine the ampere turns lying within the angle AOC plus BOD, which are the demagnetizing ampere turns. So if we calculate their value, it comes out to be IC Z into 2 theta over 360. So if we calculate the demagnetizing ampere turns per pole, so it would be ICZ over 2, we will divide it with 2. Here we have total ampere turns per pole, we have done it. So we can calculate with for demagnetizing ampere turns per pole. So it would be ICZ theta over 360. So now these are the ampere turns per pole for demagnetization, like this is the one. So once we found these out, then we can also calculate this remaining one, which are for cross coupling. So cross magnetizing ampere turns per pole, they would be ATC. For cross coupling, they would be total number of turns per pole, total ampere turns per pole minus the magnetizing turns per pole. We have already determined these values. So we will put this value ICZ theta over 260, 360, and we can find out this value. So by using these formula, we can determine both the number of turns, the ampere turns per pole for this demagnetizing turns, and for cross coupling number of turns. So thank you very much for this was the today's lecture. So Agus, can you upload these?